AP Chemisters, this is Mrs. Vanderlei bringing you section 8.9 blank ball video. This is the last section in chapter 8, and it kind of wraps up the idea of periodic trends. So we had said earlier, I think it was in section 8.5, that the alkali metals are highly reactive. Now we know why. We know that they have only one valence electron. It takes not too much energy to take one electron away, and therefore it has a very high metallic character. We'll talk about the halogens, which are group 17. We know that they have very high ionization energy, but they have very high electron affinity. They love those electrons. They're very exothermic when they grab those electrons. And then we also know some of the noble gases. So let's just begin with the alkali metals. As you go down the column, the metals are going to react more vigorously. Okay, so here's my reaction. We have a balanced chemical equation. The X2 will be, let's say, chlorine or fluorine or something, and one of the halogens, if you will. And so we have M is any alkali metal, and the X is your halogen. I want you to watch this video. I think you're going to like it, and write down your observations on what happens at this video, and then come right back. So what did you notice when they put the alkali metals in water? Wasn't that fun? What are we going to make? Well, we are making a hydroxide out of this, all right, and they're soluble, so they will dissolve in water. That's why we wrote them out as ions. But what else are we making? We're making hydrogen gas. So you may wonder what caused maybe some of that explosion that you may have seen. It was the hydrogen gas that was exploding. The halogens are your most reactive of the nonmetals. So again, we have any kind of a metal plus your halogen. You make the metal halide. So it says write the reaction of iron and chlorine. So here's my Fe. And chlorine, remember, is a diatomic gas, and we are going to assume we're making the Fe3+, so FeCl3, and now we got to balance it, so I'm going to put a 3 here, I believe, and a 2 here, and a 2 there, and there we go. Okay. Write the balancing chemical equation for each of the following reactions. I tell you what, why don't you try this, and then we'll come back. All right, let's see how you did. Well, here's my potassium. Here's my bromine. Okay, Br2 is another diatomic. And I will get the potassium bromide. So that's KBr. Notice that this is a +1 and this is a -1. So that's the correct formula. And then we need to balance it. Rubidium, that's Rb, and liquid water. So H2O. And what am I going to make? Well, this is a single replacement, and the hydrogen is going to create hydrogen gas, but this is where if I ask you this, let's say on some kind of test or something, people are going to make mistakes. You don't make rubidium oxide, you make rubidium hydroxide. Now rubidium, as you know, is in group 1, and so its charge is a +1. Hydroxide is OH, which is a -1, so that's the correct formula, and then you get H2 as a as what is being replaced by the rubidium. So now we have to balance this. I believe we need a 2 here and a 2 here and a 2 here. What would also be good at this point is probably to separate them out into their ions. Because as you know, rubidium hydroxide, group 1 hydroxides are going to be soluble. So you're going to write out their ions. All right, what about the next one? Gaseous chlorine and solid iodine. We don't see that every day, do you? So Cl2 plus I2. This is a gas. This is a solid. All right, and I believe we're going to make Cli, and we're going to make 2 of those, okay? And how do I know that's what I'm going to make? Well, you can draw your Lewis dot diagrams for those, but wait a minute, that's the next chapter, so maybe you can't. That is what you're going to make, Okay. Now, what do you know about your noble gases? The smaller noble gases are very unreactive. They are so unreactive they just can't, okay? So if you look at the ionization energy and electron affinity of those, they just don't even exist. As of right now, that, you know, in our technology and whatnot, there are no known compounds of helium and neon. Some of the larger ones, yes, you can. So why is that? Okay, why can argon, krypton, xenon, radon, why can they react? Well, it says look at their orbital diagrams. Okay, let's do that. So argon is like 1s2, 2s2, 2p6, keep going, 3s2, 3p6. Okay, so here I have my 1s, they want orbital diagrams, 2s, notice I'm putting blanks underneath my arrows, 1, 2, 3, 2p, up, 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 down, 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 3s, and 3p. Now, that didn't turn out too well. There you go. You may wonder, okay, what's the big deal about my orbital diagrams? I just made them. They're filled. That's why they're so stable. Why can't argon react? Well, what's there that I didn't put in? What is also in the third orbital, or the third shell, if you will, that I didn't put in there, that right now is being very unoccupied, and that is your 3D. It's there, but it's not being used. I have an empty 3D orbital that I can still use. So what can happen if you want argon to bond? Some of these electrons here, well, just maybe 2 of them, can be what we call promoted into the empty 3D shell. So if I would like to bond argon with, let's say, 4 fluorines, all right, I will promote 2 of these electrons. So hang on a second. Let's go backwards. Oh no, what's happening? Okay, so here we go. Here's my argon, and like I said, I have this empty shell. What if you want argon to bond with some fluorines? Let's put it that way. Well, what can happen is that we can actually promote one of these down arrows, and we can put it in the empty D shell. Here's my 3D. So now I have a spot here and a spot here in which it can react. So krypton has the same thing. Krypton has an empty 4D shell. Xenon has an empty 5D shell, and radon has an empty 6D shell. So those empty orbitals that are there but aren't being used at that point can allow for reactions to occur. So let's go back and talk about helium and neon. Why is it to this date, let me extend this, to this date that helium cannot bond? Well, helium is 1s2. Is there anything else in that first shell available for helium? Absolutely not. What is there? You only have 1s. There is no such thing as a 1p or a 1d for any electrons to be promoted to. What about neon? Neon is 1s2, 2s2, 2p6. If we want neon to, let's say, bond with fluorine, is it possible? The answer is no. Why not? There is no empty 2d orbital for the electrons to jump up to and free up and bond. So that's why helium and neon to this day has never ever been made to react with something else. There is no room for them to react. There's no empty orbitals in which to use to make them react. So that concludes the Chapter 8 notes for right now. I hope this was helpful. I hope you liked the little video that you got to watch at the beginning. It was pretty cool, wasn't it? Actually, no, it wasn't. It was pretty hot. So anyway, hopefully that helps, and don't wait to be great. Bye.